So, we understand that for a manipulator we want to start from a position, initial position, and move to a final position. So, initial we know where it is, for the final one we know we can find out where it is and we can do inverse kinematics. So, we can move all the joints so that it goes there. And but going from position to position, there is always a time factor, right? How quickly do we need to go there? If it's too quick, if you command motions which are very quick, then the actuator may not be able to take it up. If it is very slow, then you will not, your payback period for the robot goes up very high, right, or may not fit in the process. So, and then there are other things. So, that is pretty obvious, but then there is this part about slightly more subtle. If you move in very fast modes, you can also excite some resonant modes in the structure. Okay, so, then it starts vibrating and things like that. So, these are actually catalogued. So, if you are working on a real robot, it will work around these kind of issues. So, it will not allow some joints to go at some angular velocity, so that you do not get the corresponding vibration in the arms. That is why you pay so much money for a robot. You can make one much cheaper, right. Everybody says, this one costs 30 lakhs, I can make a similar one for 5 lakhs. Yes, you can make one, but it is not usable out there on the field because of all these issues. Now, so there are two terms which I have used up here, one is path and one is trajectory. So, a path is essentially a locus of points, okay. And then there are two things which I have used here, joint space or in the operational space. Operational space is quite easy to understand. If I say that I want to start from here and I want to be here, this is just 2 points, okay. But then if I say, okay, I want to go this way, then I get a locus of points. Okay, I want to go from here to here, so I have a locus of points. In joint space, it is little more difficult to visualize, because correspond to each of these points which I have here, there will be for each of the joints, there will be a particular value of the angle theta. Okay. Now, so successive values of theta essentially form a locus. It is very difficult to see, usually when you want to see a locus, you want to see it in 2D space. Okay, you need two coordinate axes, right. Without a coordinate, on a single coordinate axis, it is difficult to visualize a locus. So, in case of the joint space, the locus is visualized with the rotation on the vertical axis and maybe time on the horizontal axis. That then gives you a locus which you can visualize. So, conventionally a path is a pure geometric description of motion. Now, starting from this, if you take a path which is a pure geometry, so go from here to here, so this is just a locus, and then you specify a timing law that okay, you go at this point 1 second, here you be at 2 seconds, here you be at 3.7 seconds, here you be at. So, when you combine these two, you get what is called a trajectory. Okay. It's a very simple and a very fundamental definition which you need to understand. Is that clear? Okay, so, timing law. Now, the timing law need not be explicit. If I say okay, I want to be at this point, this point, this point, this point, and I start saying at this point I want the velocity to be this, then I am implicitly specifying a timing law, though not explicitly. I am not saying that I want to be here at this time, but if I specify the velocity here and I also specify the velocity here at the next point, that means I mean there is a bound. Theoretically it is possible that in between these two I could have taken a very large amount of time. So I could have started from here, and from this velocity I could have decelerated rapidly to near zero velocities. I could have just sat, creeped slowly, and then finally when I come close to this point I accelerate very large amount, so that at this point I arrive with that particular velocity. But that's ridiculous to do, right? So when you specify velocity and acceleration at each point, you have an implicit understanding of trajectory, though it is not explicit, and though theoretically there are many things possible in the middle. For practical purposes, it is a trajectory. Now, so this whole set of 3 lectures that we will have on trajectory planning is to generate reference inputs to the motion control system. Now, the motion control system, you have a motor of some kind which you are trying to control, give velocity, give voltages to the motor or give current to the motor depending on which mode of control you are on, okay, so that the end effector moves in the right fashion. Okay. So, this is also true of whether you are working with a parallel manipulator or a serial manipulator. Anything that you do is broken up into these basic steps. Now, so what you then do is you typically generate, so instead of saying that okay I have point here, point here, point here, point here, this time, it is very difficult to run the controller on the basis of that. So what you try to do is you generate interpolating functions, typically a polynomial for the desired trajectory. And then there are 2 classes. One is when you do point to point motion, when only the initial and final point of the paths are assigned, or you can go through a sequence of points. So when a finite sequence of points are assigned along a path. Okay. So I am still not talking about saying that I want to go on a circle, I want to go along an ellipse. Okay. That is a different point, that is a different task altogether. I am talking about given a finite sequence of points that here, 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 here. Why are those 2 different problems? So if I have a circular path saying here, 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 as opposed to saying I want to go on a circle, why are they different tasks? Any idea?
So the computer will consider a large number of points when we are talking about the circle.
Okay, can you do anything better? We have all used computers, right? You have drawn a straight line.
If specific points are specified, then it moves in chords.
Moves in chords. It could move in chords, but I am already telling you that I will do polynomial interpolation. So it does something, it uses a polynomial of some kind. So you all drawn straight lines, right, using your word drawing tools or something, or AutoCAD. So how do you think a line is drawn on AutoCAD?
Sequence of steps. Sequence of steps.
Sequence of steps. So there is something more than that, right? Because suppose I have a line, okay, line is still, suppose you draw a circle and then you zoom into one part of the circle. What happens? Really?
No, if it's vector graphics, then the resolution is infinite. The more you zoom in,
The more you zoom in, the better and better it becomes, right?
if it's raster graphics, then you have
Yeah.
to start seeing the pixels.
So why do you think that happens?
Because of the way it's defined.
The way it is defined. So in vector graphics, you define it is actually intrinsically defined as a circle, and what you see on the top is what is called a rendered image. And so there are magnificent algorithms designed 40 years ago which can very quickly find out which pixels correspond to that circle. Okay. And they are very fast and they are so efficient that they actually are written into the hardware now. So it is just there in the chip, in the graphics chip. So now they do a lot more. So, if you are drawing a straight line, it is done very similarly. They do it for ellipses and cubics and lots of other things now. So, that is what you call a graphics card or a graphics engine. Okay. So, that is a different deal. So, you can actually, in addition to what I am going to teach here, you can have these kind of circle, ellipses, special curves depending on what you are trying to do. So, that you can program separately. So, those interpolations. So, then it will operate at the resolution of the robot. So, we are not talking about that, we are saying okay, I am specifying a finite sequence of points. Okay. Now, why do you want to do that? Except for some free cases like circles and straight lines and ellipses, you cannot specify a geometric path fully, especially on the work floor. Right? If somebody is actually programming it, it's very difficult for them to fit a curve polynomial, or he will not know why is, suppose I say okay, move from here to here in the least time, he will not know what to do. Okay, so, you can derive given the maths. So, that is one issue. This second thing that you want to do is sometimes you just want to say that okay, you start from this point and you go here, and I just want you to go past this point or come close to this point. That is just a specification. Okay, so, maybe you have picked up an object, and then while going to finally inserting it, you want to take it past a camera which reads up the part number, and then you can connect it to a MIS or something which will check and tell you what is the, it is just a double check on the right part number in electron, you can match it and see what happened, okay, or which batch number it is. So, you have these kind of specification, and sometimes you can say okay, you go from here to here in a straight line, here to here in a circle. So, you have that kind of situation also. So, both cases. And similarly, when I am talking about a trajectory, so this last part, usually will not specify, will not say come here at this time, come here at this time, but you will usually know that I want to go from here to here in this amount of time. What you might want to then say is that okay, you limit the velocity to this value, you limit the acceleration to this value, okay, and you ensure continuity, ensure smoothness. These are the kind of parameters which you look at when you specify the trajectory. So, then this overall concept of the joint and the operational space. You have single axis motors, so control finally has to be done there, and I call that the joint space. And if you have data in the operational space, you can do inverse kinematics or you can do Jacobian control, you can bring it down to the joint space. And but you can't just deal with it. Now, you need to sit in the operational space, because if you have stuff like obstacles or some path constraint, you simply do not want it to go, suppose you want to go from here to here, you do not want it to go past this, you say okay fine, you go like this. So, you will give a via point here which will take you there. Now, these kind of data is usually better specified in the operational space, though theoretically you could always convert this into joint space by doing inverse kinematics. From a usability point of view, it is not good. So, you have to keep moving between both of these domains, and there are some constraints which is just simply difficult to define in the joint space. Suppose you say roughly I wanted to pass through this circular area. Now, converting this circular area into a corresponding definition in the joint space is difficult, because there are co-links together. So, if you say okay, I wanted to go through this general circular area, if you have a single point, you can map it into joint space. But if you have a looser definition that I wanted to go somewhere in this circular patch, a looser definition, then this circular patch theoretically you can map into a corresponding definition in the joint, except that they will be linked together. So, they are not unique values in the joint space. So, it is simply difficult to do so. So, we need both, and today's lecture we will start with joint space trajectory. Okay. And one of the other issues that you need to remember is there is something called a teach pendant. You saw that for the KUKA, right? You can hold that thing in the hand and you can just move it. So, one of the easiest ways, instead of specifying in coordinate systems, you can take the robot and you can use the teach pendant and you can move it and make it touch a point here, and it says store. You move it manually, take it to another point here and you say store, and it's okay, now move from here to there, from a stored point to another stored point. Or you can take it from here to here, you can move it here and then you move it there and you say okay, you store all these points. Now, when you do this at each of these locations, when you use something like a teach pendant, the individual joint values can also be stored. So, you do not always have to do inverse kinematics to get the joint space interpolation points. Okay. Now, so what is the basic idea? They need a planning algorithm which generates a function qt, okay, interpolating a given vector of joint variables at each point in respect to the imposed constraints. So, this is the mathematical definition. Okay. So, what are a couple of features that we want in this? We do not want to do too much computation. Why? We want to write it into hardware, very simple. So, I might actually from the computer I might interface with the motor driver every maybe at 60 hertz, 50 hertz, but the driver runs this its loop at typically megahertz range, okay, closes the loop in a megahertz range internally with the motor. So, most of these computations that I will discuss today, they are actually done on hardware. So, I do not want it to be very complicated, because then you have a problem. And you want the joint position and velocities to be continuous function of time. There is no reason why you do not want accelerations to be computed to be continuous function of time, so that you do not have any jerks. But usually these systems have some built in compliance for stability, and that takes care of the jerk. And essentially visually you cannot detect, you can detect velocity discontinuities, but you usually cannot detect acceleration discontinuities visually. Okay. Do you understand the difference between the two? So, if you see something, if there is a strong velocity discontinuity, you can see it visually, so standing from far, but you cannot see acceleration discontinuity. So, that is why this choice. Okay. So, you can what you do is you just usually impose only continuity of acceleration, which essentially is same as velocity discontinuity, you inhibit that. And what you do is it is enough to just analyze what goes on for a single joint variable qt, right. Those are 6, 8, 9 joints depending on what your system is. If you just look at one joint variable, it is okay, because you would assume that all the joints will complete the motion in the same time t. Okay, then you go from, otherwise it is very funny. If I want to go from this position here to this position here, if I first do here and then I am sitting here and just doing this, it is not the right thing to do. Does not look visually right, it actually is not energy efficient, so on and so forth. So, usually you will do this in one shot. So, it is okay to look at only single degree of freedom and then we can go across. So, the first case we look at is point to point motion. We go from initial to final joint configuration in a time Tf. So, one to other I specify the time, because I am doing with the trajectory, and so obviously the path is not unique, right. I can move straight line, I can move like this, I can go like this. So, so idea is that you have a trajectory which also optimizes something or the other, right, to just something more. So, if you say okay, I want to go from here to here, any kid will tell you okay, go on a straight line. Is that the best thing? Perhaps not. So, we need to have a look at it. So, we want to look at optimize some performance index. When I move the joint. So, that brings in the concept of optimal trajectory. Okay. So, if I is the moment of inertia and I want to go from angle, take the angle q from initial value qi to final value qf in time tf. Okay. So, obviously infinite solutions exist. Now, if I am executing this motion through a torque supplied by a motor, first question I can ask is find a solution which minimizes the energy dissipated by the motor, or it minimizes the torque applied by the motor. So, I have many such, I could employ one of the many such concerns. If I am minimizing the torque, what is my advantage? It will just minimize my load, so my vibrations, the peak current consumption, so my load downstream. If I am a green person, I will say minimize energy consumed. Okay. So, obviously you have to formalize it, right, otherwise I would not be teaching it here. So, you have a simple differential equation I omega dot is equal to tau, right, and then I have a condition that omega t dt integral of that 0 to Tf has to be Qf minus Qi. I need to cover that amount, and then I say okay fine, I minimize the square of the torque. Why the square of the torque?
So that it's always positive.
It is always positive, right. It is called the Euclidean norm. Do you know of any other norm? What happens if I make t, if I raise t to infinity, then what happens?
That's taxi cab.
Huh? And that is called the infinite norm. So, what will that do? See, this gives you a kind of RMS, you know also this as the root mean square, right. I mean this is equal, you are not taking the root but the square. So, it basically takes the integral, but if you take it, raise it to the power of infinity, then the dominant term becomes, which will become the dominant term? The largest value. So, the whole integral is dominated by the largest value. So, it essentially then if I were to minimize t raised to power infinity, it will just try to get the largest value down. So, that is also possible, that is called the infinity norm. Okay. Little aside, when you get out of IIT you should know about what an infinity norm is, though you will not know how to use it, but you should know that it exists. So, so what this does is it limits the magnitude of the torque in one particular, in the RMS sense. If I raise it to the infinity, then it will reduce the peak torque. So, that is why I have written some sense, you can just change the index here and you can change the performance measure. So, when you do this, the solution is all this type, you can show that it is of the type omega t is equal to at square plus bt plus c, very nice, right. Then it becomes a polynomial, quadratic, and we know all about quadratics. We know all about it? Quite a bit. So, then I can junk all this, right. So, once I do not actually have to solve this equation subject to this condition with this, once I do not have to do all of these things and I tell you that okay, solution of the type omega t is equal to at square plus bt plus c, then I am back to class 12. So, that is what we will do for the rest of the class. Oh, I forgot this last line, only small catch. The moment of inertia seen at a joint, so this, I mean, the solution being of this type is valid for a constant I. Now, the moment of inertia seen at a joint is not constant, right. If I have this joint, if I have my arm extended, then the moment of inertia, and I have a mass here, the moment of inertia has a large momentum corresponding to this. On the other hand, my hand becomes like this at this joint, moment of inertia is different. So, in that case, this is not the solution. Okay. So, we will have to revisit this after we have learned dynamics, okay, this possibility. So, I do not know whether we will manage this semester, but otherwise I will send you to people like Ayan Carr or Mashuk Nabi in electrical engineering, who love doing this problem with a variable I. Okay. So, you put it in this form. So, if you take the trajectory is given by this, the velocity profile is this, linear acceleration profile. You want to identify the polynomial. Polynomial has 4 coefficients, and you have initial and final joint position values qi and qf. Definitely you have to impose that. Usually you will start and finish at rest. So, you have 0 velocities there. Okay. So, essentially A0 is qi, A1 is qi dot, and then you have, you write this, instead of t you put in tf. So, you get qf here, then again put this, you get qf dot, solve for it, right. So, you can get all 4 coefficients and you know the polynomial. So, so I am going from 0 to pi, and with 0 start and finish velocity I have just extended it a little bit beyond 1. So, the velocity has a parabolic profile, acceleration has a linear profile like we all predicted, nothing great about it, and with this discontinuity at 0 and 1. Okay. The velocity does not have a discontinuity, the acceleration has a discontinuity. So, this is trivially simple. Okay. Finally, getting this. Okay. Now, if I want to also control the acceleration, I do not want the jumps, and I want to actually control the values, they need at least a fifth order polynomial. Okay, so that you have 6 coefficients, you have 6 constraints, so you need 6 coefficients. So, you need to go to a 5th order polynomial. So, impose the condition that 0 and tf, and you can solve it. The only catch is we then have to give up on the performance index. So, you do not have this nice option of saying that I am going to control the peak torques. In fact, that is the catch of this whole trajectory planning thing. So, given large number of points, so far when you always talk about a fit through it, right, you can always find a fit by going to higher and higher order polynomials, and if you go to higher order polynomial, if you use any index for it, you know, like any, what are typical indexes which you use to find out the fit? R square, okay, find it out. If you keep increasing the number of polynomials, your fit will improve, right. But here it is not desirable, because you know that the second order polynomial which defines the velocity is the one which minimizes tau squared for a constant I case. Other one is too complicated to comment on right now. So, if I try to fit the acceleration, I am going into a 5th order polynomial, it is not right. It is not okay from the torque point of view. In fact, if you try to match the acceleration, what will now happen is that your peak torque values will keep jumping up and down. So, it is not desirable. So, though you can fit the acceleration, it is not desirable from a practical manipulator stand of view. Okay. So, what you do is in industrial practice you do this thing called blended polynomials. So, you can then know immediately whether this is can be the trajectory that you are generating is guaranteed to be supportable by the manipulator in most cases. So, what you do is you assign what is called a trapezoidal velocity profile. Let me take a peek sneak, okay, the previous slide first, I will come back to this. So, what you are saying is that I want to cap the velocity at some value. So, what I am going to do is I am going to go up the velocity on a linear ramp, okay, with a constant value of with the limiting value of the acceleration. Once here I am going to cruise at the same velocity and then I am going to come down. So, this is the structure which we call the blended polynomial approach. So, it starts with a constant acceleration in the start phase, a cruise velocity and a constant deceleration in the arrival phase. And so, if you look at the trajectory, that is a this is the linear segment and then there are two parabolic segments, a parabolic segment here and a parabolic segment here. So, the formulation goes like this, you formulate by assuming that the final time of trajectory duration has been assigned, and usually you will assign the velocity that I talked about not by specific absolute velocity, but usually in percentages of the peak velocity that can happen at the joint. So, that is very safe and gives you an estimate of how much you are loading the joint. And if you reduce the motion duration, you will require large values of velocity and or acceleration beyond those achievable by the manipulator. Okay, so, you do not want to do too short a time, and you also kind of assume that the acceleration deceleration portions are very similar, again that becomes simpler, and the function is symmetric trajectory with respect to the midpoint. So, you have to calculate only 1/2 and you can reflect it about the midpoint. Now, you have done this somewhere before, where? Do you remember at all? Similar thing. Cams, in the cam profile, the rise and the return, they are actually very similar. I mean, this should have immediately reminded you of those curves, okay, except you would not have done the blended polynomial curve in the cams. So, this is very similar to that. So, we will just stop here today. I mean, have not done much mathematically, but hopefully you are getting the hang of things as to what do we want to do. So, in the next class we will take out from this and we will look at how to connect when we have given multiple points instead of just given Qi and Qf. If I now have some number of points, how do we do it? And you can expect mathematics gets a little bigger. It will become an n point problem. Each is still polynomial, so it is not that difficult, but you just have to handle it in a matrix approach, and they are interesting algorithms which one needs to know.